Good day, students. Welcome to part 5 of the Geometry Regents review for January 2014. We're going to be working on problems 21 to 25 in this installment. The rest of those videos can be accessed to mathgotserved.com/testprep.html. Alright, let's take a look at problem 21. It says the coordinates of point P are 7, 1. What are the coordinates of the image of P after a rotation of 90 degrees about the origin? So we're manipulating, or we're carrying out a transformation on an object, a point, located on 7, 1 by rotating 90 degrees. So anytime you're dealing with any shape or object that's presented in word form, what you want to do is give yourself a visual so you can have an idea as to what's going on. So I'm going to plot this point, this object that we're translating, that we're transforming. So what we're going to do is graph our x and y coordinates. So this is our x-axis and this is our y-axis, and 7 on the x, 1 on the y. 1, 2, 3, 4, 5, 6, 7. So this is 7 and this is 1 right here. And the point, the object we're dealing with, is located here. That's point P. Now, if we rotate this point 90 degrees about the origin, where on earth is this point going to land? We know that rotating 90 degrees is going to take us in this direction, 90-degree rotation like this. So where is this point going to land is the question. The easiest way to rotate an object, to graph a point, an object after rotation, is to rotate the axis. Okay? If we rotated this x-axis by 90 degrees, where is it going to end up in? This image is going to end up right exactly where this y-axis is. This axis will end up right here. So this 7 will be graphed right here. 1, 2, 3, 4, 5, 6, 7. So that will be where the one of the coordinates for the point. 1, 2, 3, 4, 5, 6, 7. What's going to happen to the y-axis? The y-axis will also rotate 90 degrees also. So this piece right here is our negative x, but when we rotate under 90-degree rotation, this is going to become our y image, our new y. Okay, so in our old y we went up 1, but under this rotation we're going to go up 1 in the direction of our new y, and that's going to take us right here, -1. So our point under 90-degree rotation is going to be right here. Okay, so all we just did is we imagined rotating this entire quadrant 90 degrees. So instead of going 1 from the x, we're going 1 from the y, heading 90 degrees upwards. Okay, perpendicular to the axis. So this is our new point right here. This is P, and this is P prime under the image of the 90-degree rotation, and its coordinates are -1 and 7. Alright, then the answer is option number 4. So the key takeaway in this problem is give yourself a visual and rotate the axis. Don't try and rotate the points, that's too difficult. Rotate the axis and then preserve your movement in that direction on your new movement, on your new axis, and then that'll be easy for you to graph your new points. Alright, so that's that. Now let's take a look at problem 22. It says lines P and Q are intersected by R as shown below. If angle M is 7x minus 36, and measure of angle 2 is 5x plus 12, for which value of x will P be parallel to Q? So if we want line P and Q to be parallel, then these two angles will have a special name, okay? And then a special connection also. What are these two angles called? Let's mark them. These two angles are known as same side interior angles, okay? Angle 1 is 7x minus 36, and angle 2 is 5x plus 12. Now, these are same side interior angles if you have two parallel lines cut by a transversal. Same side interior angles are supplementary. Okay, what does that mean? It means that they add up to 180 degrees. So measure of angle 1 plus measure of angle 2 is equal to what? So they're supplementary, they add up to 180. Okay, if you think about it, this angle right here is corresponding with this angle, and then this angle and this angle form a linear pair, which is 180 degrees. So that's how we know that these two add up to 180. All right, what we're going to do now is set up an algebraic equation. So we have 7x minus 36. That is the value of the measure of angle 1 plus 5x plus 12. That's the measure of angle 2. They both add up to 180. So if we can solve this resulting equation for x, that will be the value of x that ensures that p and q are parallel. So let's combine like terms on the left side of our equation. 7x plus 5x is 12x. And then negative 36 plus 12 is negative 24 equals 180. And then we we add 24 to both sides. Add 24. And then we have 12x is equal to 204. And then to finally isolate x, we divide both sides by 12. And then you have x is equal to 17. All right, so our answer is option number 1. All right, let's look at 23. It says, what is the equation of the circle with its center negative 1, 2 that passes through the point 1, 2? Okay, now this is another problem involving the equation of a circle. The equation of a circle in standard form, as illustrated in these options here, is x minus h squared plus y minus k squared equals r squared, where the center is given by hk and the radius, of course, is r. Now, so this basically tells us that in order to write the equation of a circle in standard form, you need the center and radius. That's all you need, center and radius. In the problem, they gave us a center, which is nice. The center is negative 1, 2. That tells us that h is negative 1 and k is 2. How about the radius r? What is our radius? We have absolutely no idea what the radius is. So how do we figure out the radius? Well, it tells us where the center is. It also tells us a point that the circle goes through. Now, if you take a close look at these 2 points, what do you notice? What you notice is that the x-coordinates of the points are the same. I'm sorry, the y-coordinates. The y-coordinates are the same. So since the y-coordinates are the same, this means that we're just moving in the x direction. From negative 1 all the way to 1 would tell us the measure of the radius. So if you go from negative 1 to 1, you go negative 1, 0, 1. That's 2 units. So our radius is 2. Okay? But in order for us to determine lengths of portions of a shape, given in word form, it's beneficial to give yourself a visual. When you do things mentally, you're taking a risk and you can make mistakes, all right? So always give yourself a visual whenever you're trying to label or find parts of a geometric object, okay? So I'm going to graph this entire circle and show you that the radius is actually in fact 2. So we have the circle there. Let me just shift this up a little bit. Okay, so the center is at negative 1, 2. Let's go ahead and graph that. Center is at negative 1 and 2. And then it goes through the point 1, 2. So 1 and 2. It goes through this point. Do you see what the circle looks like based on this given information? This is the center, so just draw a circle. Bam, there you go. Now, can you see what the length of the radius is? The radius that I was calculating earlier, I was calculating this displacement right here, this length. So going from negative 1 to 1, that's 2 units long. Okay, that's 2 units. So that tells us that the radius is equal to 2. So you see how easy it is giving yourself a visual? If you give yourself a visual, it's very accurate and less complicated to determine missing components. Now that we have h, k, and r, we're simply going to plug them into this equation, h, k, and r, and that will be the equation of our circle. Okay, let's go ahead and do that. So we're going to have x minus, now this is a very important tip. Anytime any of these numbers are negative, please do not just put them here without the sign. You have to include them with their sign. So this is -1. Guess what I'll put here? I'll put parenthesis -1. Okay? Square plus y minus k, which is 2, is equal to r squared. Do not forget to square this number. That's one big mistake most students make. They just put the radius there and they forget to square it. The formula calls for you to square the radius. All right. Notice these two distractors, they're designed to catch people who forget to square their radius or who mess up the sign. Okay. All right. So if we simplify this, we'll have x plus 1 square plus y. Where's my square right there? Plus y minus 2 square equals 4. All right, and our answer is option number 1. All right, let's take a look at problem 24. So it says in the diagram below, diameter AB bisects the chord CD at point E in circle F. So if AB bisects CD at point E, then that means that this side is congruent to this side. Okay? All right. It says if AE is 2, so this portion right here is 2, and FB is 17, so 17, find the length of CE. All right? So how about we call the length of CE X? Now, anytime if you see a circle with 2 intersecting chords, you want to think about the intersecting chords theorem. Okay, so if you have 2 intersecting chords like this, I'm sorry, if you have a circle with 2 intersecting chords, so we have one chord like that and the other like that, okay? And you have lengths, so let's call this A, B, and then here is C, D. All right, do you remember what the intersecting chord theorem says? Well, it's the product of the chords that's been separated by a point of intersection. The product of the length of the chords is the same for both of the chords. So this chord, A times B, is equal to this chord, C times D. All right? So that's basically what the intersecting chord theorem says. So in this situation that we have here, this little piece, AE, is times this big piece, EB, is going to be the same thing as CE times DE. All right, so we can say AE times EB as a longer chord. The product of that is equal to the product of CE times DE. So this is based on what the intersecting chords theorem tells us. Okay, so using that, let's see. We know that AE is 2, so we have 2 times EB. Now, what is EB though? If from F to B is 17, so this entire length, is 17, then how long is EB going to be? EF going to be? So this entire length right here is 17. Let's see. We know that if we go from, we know that FB is the same thing as FA. What are they? They are the radii. Okay, this is one radius, and that's another radius right there. Okay, so AF is equal to BF. All right. We know that AF is made up of 2 pieces, right? AF is AE plus EF. And we know that BF is 17. AE plus EF add up to give you 17, right? So if AE is 2, how many more do you have left to make the entire thing 17? Basically 15, right? So let me show you here. A is 2. 2 plus some number EF is equal to 17. So EF, you subtract 2 from both sides, must be 15. Because 15 plus 2 is 17, which is exactly the same thing as this, BF. They are both radii of the same circle. Okay? So EF is 15. So we have EF and FB. So EB, the entire EB is 15 plus 17. 15 plus 17 is 32. All right? So we have that down. Now, let me just write it here. EB is equal to EF plus FB, which is equal to 15 plus 17, which is 32. All right? Now, CD and ED, they're congruent, right? If CE is X, then DE must be X also, right? So what I'm trying to do here is I'm trying to set up an equation that I can solve using algebra. Okay, so CE is X times DE, which is X also. So we have the equation 64 is equal to X squared. So do you see what the answer is? To get X isolated, which is the measure of CE, we root both sides, and then we have X is equal to 8. So our answer is option number 2. So don't forget the intersecting chords theorem. Okay, if you have two chords intersecting like this, then the segments on the same chord, if you find a product, it's going to be equal to the product of the segments and the other chord. Okay, so that's the whole idea behind the intersecting chords theorem. Now let's take a look at the last problem in this installment. It says, which quadrilateral does not always have congruent diagonals? Well, this is easy to do. You just want to exhaust possibilities here. Just simply draw all the quadrilaterals and see which one does not always have a congruent diagonal. So if you think about an isosceles trapezoid, the two sides are always the same, right? So no matter how I stretch this, guess what? They are always going to be the same. So this is an isosceles trapezoid. If it's isosceles, that means that this side is congruent to that side. Okay? 1, 2, 3, 4. 1, 2, 3, 4. Perfect. So look at the diagonals here. You can just by inspection, you can make an educated guess as to the measure of the triangle. So look at these two triangles right here. You can clearly see that the diagonals are congruent, right? These two triangles are congruent triangles. Okay? All right. How about so this is isosceles trapezoid. Isosceles trapezoid. Isosceles trapezoid has congruent diagonals. How about number 2? So isosceles trapezoid is good. Number 2, rectangle. Is there a way where you can draw a rectangle in such a way that the diagonals are not congruent? The answer is no. There is no way you can draw a rectangle without the diagonals being congruent. It's always going to be congruent. Okay, so for a rectangle, just draw the diagonals. And it's easy to see that there isn't any way you can morph this rectangle in such a way that the diagonals are congruent. So the diagonals are congruent here. Hopefully you know what the diagonal means is the segment that connects these two vertices that are opposite each other. The rectangle is good. Diagonals are congruent. Remember, we're looking for the diagonals that are not always. They could be sometimes, but not always. 3, rhombus. Rhombus just requires that the four sides of the quadrilateral be congruent, right? So the question is, can we draw a rhombus in such a way that the diagonals are not congruent? All right, so I'm going to draw a rhombus for you, and then we can do some inspection here. So guess what? This is a rhombus, and that's a rhombus. If I remember that a square is a special case of a rhombus, right? If you had a square, the diagonals will be congruent. But what if we have something like this. What do you see happening? One of the diagonals is getting shorter and shorter, the other one is getting longer and longer. Okay? So in the case of a rhombus, the diagonals are not always congruent. It's only when the rhombus is a square. That's the only time that the diagonals will be congruent. So you can see that this segment right here is not congruent to that segment right there. Okay, so let's go ahead and write some statements real quick. In this case, let's call this A, B, C, D. So in this case, AC is not equal to BD. In this case, A, B, C, D, the diagonal AC is equal to BD. That's why it passed the test, right? And in this case, A, B, C, D, this one also, AC is equal to BD. All right? How about a square? We know that every square is a rectangle, but not every rectangle is a square. A square is a special case of a rectangle, so since a rectangle has congruent diagonals and a square is a rectangle, we can just conclude that the square automatically has congruent diagonals. All right? Well, if you want me to show you, it's pretty straightforward to see that no matter how you draw a square, the diagonals will always be congruent. Okay, so let's go ahead and show that to you real quick. So little square, big square, the diagonal is always congruent. Okay, so let's show you now. Connect it right here. There you go. Those are the diagonals of our square, and they are always congruent. So we have A, B, C, D. So we have, in this case, AC is equal to BD. Diagonals are congruent. So this passes. The only one that fails is the rhombus. So our answer is option number 3. So thanks so much for taking the time to watch this presentation. Please feel free to subscribe to our channel. We really appreciate it. And do post a comments to let us know what you think about this clip. More clips coming from mathgotserved.com/testprep. Thanks again for watching and have a wonderful day.